For this section and actually the following section, we're focusing on factorisation of polynomials in C, and what that in C means is that we're looking at polynomials in the complex domain. Now we've got these sections that have come out of your textbook. I've just written some important pieces here in red that really summarise these sections. The first one here is that you've got a polynomial which we call PZ, so we'll call all of our complex polynomials PZ, and it has a power of n. Okay, so that could be 2, 3, 4, whatever power is the highest power. And you've also got coefficients here which are subscripted with an a. So an minus 1 for each power. And if we look at this polynomial, all right, if any of these coefficients, any of these are complex numbers, then we're guaranteed by the fundamental theorem that at least one linear factor will be complex. Okay, what that means is a linear factor. You've seen these in quadratics before, you know, you might have like x minus 2 and x plus 3, something like that. These factors here are called linear because they have x to the power of 1 inside each of those brackets. Linear means to the power of 1. So when we're talking about a polynomial like this, we're guaranteed if we have complex coefficients in here, so anything that has I, that are factors, will have at least one complex factor. So that's the key message here in red. Complex coefficients in your polynomial, you'll have at least one complex factor. Now really important, and here underneath as well, you can see you've got the polynomial PZ. It's been factorised into all its linear factors. Now there would be n factors for an n power up here. Now this might seem like something you know already. You know, if you have a quadratic, you can factorise it into two linear factors, but the thing is sometimes with quadratics you couldn't factorise them into two linear factors because it wouldn't work. Okay, you weren't able to complete the quadratic formula because what was under the square root was the square root of a negative number, and that didn't exist in real numbers. But now, because we're dealing with complex numbers, we're actually going to be guaranteed to always be able to break our polynomials up into linear factors. So that's really different to how things were in the real number system. The other thing that I'm looking at as well here is the conjugate factor theorem underneath, just while I erase this. So in the conjugate factor theorem, what we're told, which is really important, this is a very key thing, it's often used in exams as well, your knowledge of this particular theorem here, is that if you have a polynomial, PZ, where the coefficients are real numbers, this time, all of them real, then any complex roots that you have will occur in conjugate pairs. Okay, the reason for that is, remember that a conjugate is, for example, let's say z equals 1 plus 3i. The conjugate is z bar, and we might have 1 minus 3i. Okay, the reason that these factors occur in conjugate pairs is because when you look at these factors, and the factors for these would be z, it's always the opposite sign of what you have in a bracket. So you'd be looking at this, plus 3i. When you have these two factors next to each other, if you actually expand out, what you're going to find is that because you've got conjugates, a conjugate pair, you're going to find, we'll just do this one, z squared minus z plus 3zi minus z plus 1 minus 3i minus 3zi. So this one, you don't have to copy this one out, it's just so you can see it. And what you'll see here is that you've got plus 3i and a minus 3i, they cancel. Plus 3zi and the minus 3zi, they cancel. You've got a couple of z's left over, and you've also got here an I squared, which is negative 1. So this would be z squared minus z minus 2z, because there's two of those. And plus 1, this will become plus 9, so plus 10. So you can see here that your quadratic actually has all real coefficients. There's no imaginary coefficients here. But your two factors, which I just made up, I made these up to be factors of my quadratic, they had imaginary parts in there. So it's really, really important to know that if your polynomial has only real coefficients, you're guaranteed to have either all real, so either all of your coefficients will be real, or if you have any complex coefficients, they occur in pairs. And that's really useful because you may be able to use this key result here in red. Definitely write that in your notes and highlight it. If you're given one of the complex factors, then you can automatically know another one because you know it will be its conjugate. That's only when you have real coefficients in your polynomial pz. So it's very, very important. So I'll just show you just quickly with this example. We're going to do a bunch of examples in the following worked examples. The one I've got up here is a quadratic. Now imagine that this was an x instead of a z. Okay, and it's a quadratic you wouldn't be able to solve normally with the real numbers, but we will be able to solve it with imaginary numbers. So we're going to do factorisation by completing the square. I've got completing the square here if you can't remember how to do it. So what we do is write down the first two terms. So we're going to have z squared minus 2z. We take the second term without the z, we halve it. So we halve 2, which is 1. We add it, we subtract it, we add on the rest. Now the first three terms here will also be always be a perfect square. That's how completing the square works to make a perfect square. This is going to be z minus 1 all squared to get the minus in the middle. And what you've got left over here is plus 3. Now, in order to take numbers that are outside of the squared bracket into the squared bracket, which we can do, we have to take them in as a square root. But we can only do that when this is a negative. Okay, it has to be a negative sign for us to do that. But in this case, we don't have a negative. What we can do is we can actually manufacture a negative, because remember that I squared equals negative 1. So if we use that result, let's make that bigger, what we're going to do on the next line here is I'm going to rewrite this again. So we have z minus 1 squared. I'm going to change this plus to a minus because that will mean I can now take whatever is out here into the bracket. And I'm going to write down the 3. But because I've now turned this into a minus, I would need to multiply this answer by minus 1 as well. So it would be effectively you're doing this, yeah? So that it still looks like a plus 3. But what we can do instead of using minus 1 is we can use I and I squared, because I squared is negative 1. So now this part here that we've got outside the bracket can actually be moved inside the bracket, okay, provided we do the square root when we move it in. So I'm going to have z minus 1 plus the square root of what was out there, so 3i squared. The other bracket will be z minus 1 minus the square root of what's in what was outside. And to finish it off, I've got now the square root of 3. The square root of I squared is I. So I'm just going to simplify this. So I'll write it as root 3i, because the square root of I squared is I, and z minus 1 minus root 3i. Okay, so what we've done there is we've factorised a quadratic, which we normally couldn't factorise because we get to this point here in completing the square and be stuck. We couldn't fully factorise that into linear terms. And now what we've done is we've changed this plus sign into a minus. We've manufactured a minus sign that we want by multiplying this term by I squared. Then we can take this into the brackets and plus or minus its square root to get two linear factors. And these are linear because you've got a z, okay, plus or minus something else that has no z's in it. So both of these are linear factors. So in the complex domain, you will now be guaranteed to be able to factorise a quadratic or any polynomial into linear factors. The key thing is if you have all real coefficients, you'll either get all real factors or you'll get complex factors that occur in pairs, conjugate pairs. And you can see here, to finish off, these are indeed in conjugate pairs because check it out, we've got negative 1 plus root 3i and negative 1 minus root 3i. That's the conjugate pair. So you can always check your answer to see if you've got it right, because if you've got your conjugate pairs, it's more than likely that it's correct. So the rest of the section, we're going to be focusing on factorisation techniques for polynomials.